at, I'll search for that. Brain-inspired storage architectures, brain-inspired computation architectures we know, but storage I'll look up.
Right.
Okay. Yeah. So let's. I hope everybody can hear me. Okay. So we will proceed. We have approximately 50 minutes left for the class. So let me move through some of the sorry. Concepts. Please mute yourself if you're not asking a question. Okay. So what we are showing on this screen are some concepts associated with natural learning. Natural learning, as in, let's say a baby giraffe is born, and it is trying to make sense of the world around it. It's opened its eyes for the first time. Trying to make sense of the world around it, trying to recognize its mother, trying to move to closer to food, and over a period of, let's say, the first few days, few months, few years, it learns different skills. So I'm talking about that as natural learning. It could be for a human baby, it could be for any biological entity. So there is a predisposition that entities come with. This could be a genetic predisposition or other types of predisposition, where a species has certain boundaries within which its behavior can change, but not beyond those boundaries. And then there is a world which is giving the necessary inputs for this baby giraffe, for a baby that's walking around or crawling in the house. There is a world that is giving some inputs and feedback to this entity, the baby or the baby giraffe, which could be a positive reinforcement, which could be a negative reinforcement. But the world is providing inputs, and it is also when the baby takes a certain action or the giraffe takes a certain action, it is possible that the world gives it feedback. This could be immediate or delayed. So in some of the cases, like going and touching something very hot, it is an immediate feedback. Whereas, let's say baby takes, after the baby starts going to school, if the if the child pushes another child the first time, there may not be much of a reaction. But as they do it, then there is an overall delayed substantial reaction that comes. And that time, feedback from the world can be immediate or delayed. And then there is also a adaptation, which is central to this learning process, natural learning process, adaptation or behavior improvement over a period of time. These are some concepts connected to natural learning. The reason I list them is because I want to connect them to machine learning. So if we go into machine learning, and here I'm comparing machine learning with traditional programming. In traditional programming, you have a program. You feed some data to it. Let's say this is a program to compute tax rates, and you provide it some data, and it you have some compute on which this program is running, some compute infrastructure. And when this data is presented to the program, then an output is produced. Whereas in machine learning, this sequence is flipped. What we give as inputs are data and output. Output is optional. You don't need to give it. If you don't give it, then it becomes unsupervised learning. If you give it, it becomes supervised learning. So you provide data and output as the inputs into a compute infrastructure. And what machine learning tries to figure out is the actual program or the model which can create this output from this data. Let me give you an example to make it concrete. The data might be data of different patients, and the output may be their diagnosis. What we want to build is a program or a model which for a new patient, when their data is given, it can compute their output. It can compute their diagnosis. So we have 10,000 patients for whom we know the diagnosis, let's say the type of flu that they have had. We give both of these to a computer which should output a model. This model could be a program code. This model can be mathematical equations. It could be if-then rules. It could be a black box which just computes using some neurons and interconnections. Whatever is the model that it builds, when data about a new flu patient is given, that program should be able to output the type of flu. Output, the kind of the flu that this patient has. So that's the difference between traditional programming and machine learning. Machine learning outputs the model. Now once the model is output, see, any machine learning system runs in two major stages. One is training and another is inference. What we are showing here is training. You're giving the data and output, and you're computing what the model should be for this data to produce this output. That task is called train. Then obviously you will need to feed this program in a traditional model where this is your machine learning model. This is your input data that's coming in, and the input data is put through the machine learning model so that we know what its output is going to be. This is the new patient, and a model that is built on tens of thousands of patients. The new patient's data, when you put in, their class of flu is output. So the inferencing stage of machine learning works just like traditional programming. The training stage of machine learning works differently. Okay. I hope this makes sense to all of you. A little more elaboration into the same thing. Programming is giving a fish. Machine learning is teaching how to fish. They say that once you teach how to fish, then you can solve many more problems. It has much longer shelf life than just giving a fish, which is, once you digest it, you're hungry again. So we're showing the same thing here. There is input that's going into an information processing system. The information processing system is programmed by a user. Okay. And this information processing system processes this input to provide an output. Whereas in machine learning, the input comes in, but what goes into the system is the model that has been trained using user inputs. Typically using ground truth inputs that have been given by a human user. This will be supervised learning. So you build a model based on data, based on ground truth inputs that have been given by a user. That model is the system here. That is the machine learning system. You put input observations into it, you get outputs, just like input observations output here. But what is different is that this information processing system was just programmed by a human, whereas this learner is learned from data. Mr. Bansal?
So as you said, this will be true for only supervised learning, right? Not for unsupervised learning.
Correct, sir. So in unsupervised learning, you don't need this user. In the next slide, I'll show you the difference between unsupervised and supervised. Okay, great. Not in the next slide. One slide after. So here, I am, pictorially showing something I said yesterday. I said ML is decision automation. If you remember, I even included in the slides subsequently before uploading them that there is task automation, there is decision automation, there is conversation or interface of automation. I said that intelligent automation includes those. So we are repeating that statement that we are showing that pictorially here. There is a workflow in which there are tasks to be done and there are human decisions. So for example, this task might be read a document. I'll come to your question, Mr. Arora, once I'm done with this. Read a document, get the information from the document. A human decision might be, do we have all the fields that we need, or is the document incomplete? If the document is incomplete, you send it back. Then let's say this document is about a loan application. Then the next task can be go to a website and pull the credit rating of this person who is the applicant. So that might be the task. This is an automatable, non-intelligence involving task. And based on the application data and the credit rating, maybe there is an underwriting decision that a human takes here. I'm talking about a human workflow here before ML is implemented. ML essentially automates these decisions. So if I need to read a document and make a decision on whether all the fields are there in it or not, then there is a scope for a machine learning system here. Similarly, if I want to do automatic underwriting based on some application data and some credit rating data, then there is a scope for a machine learning model here, a regression model which determines the amount of loan that can be given to this person. And there could be similar tasks, similar decisions in the overall workflow. And our goal with machine learning is one is workflow deconstruction. That is, your entire workflow is divided into tasks and decisions. And tasks that do not involve a decision, tasks that are just computation, can be automated just through a robotic process automation or a script. This kind of tasks which do not involve a decision can be automated. Things that involve a decision require a machine learning model to be built. So your deconstructed intelligent workflows will have both tasks and decisions automated, typically conversations also automated within that. But currently we are showing ML, we'll go to conversations later. Mr. Arora.
Yeah, I was wondering, so in a human decision, a series of decisions are taken. Now, there's two ways of doing it. One is you do an automation, which is rule-based, where you say these are the rules, and basis that you automate and a decision is made. And the second is what we are talking about machine learning, where an improvement is happening with every decision. But ultimately, the machine learning model is going to learn from those either automated decisions or human decisions as to what was the basis of those decisions. So how does that actually improve? Because I think that's how the biases are also getting introduced into the machine learning and the NLM models, where because it's learning from all human data and there are inherent biases in human decisions and human interactions.
Yes.
So the first decision, sorry, yeah.
No problem. I think I got the question, but I didn't mean to interrupt you.
No, go ahead, please. That was my question.
So you're absolutely right that the machine learning model has to learn from the data that is provided to it, which either has human decisions or decisions that are based on a set of rules and automatically computed. And you're also right that the quality of the decision is only as good as the quality of data that is put in. That's what I meant when I said garbage in, garbage out. But that said, there is still a place for machine learning models because this is automation. Our goal is to be able to take these decisions faster. The purpose of automation we saw yesterday is standardization, turnaround time reduction, cost reduction, so on and so forth. Automation has multiple advantages. Scaling, we listed out 10 or 15, which I also put in the presentation. So we want to build intelligent automation systems. My point is, we want to build intelligent automation systems because they have a bunch of benefits. To build those intelligent automation systems, we need computation automation, which can be done through simply software. We need decision automation, which is done through machine learning. We need conversation automation, which is done through LLMs, and so on. So we are essentially constructing AI with all the pieces. And we are saying that if AI is intelligent automation, machine learning plays the role of decision automation. And the reason why we automate is not because you will build better systems than human decision making. In some cases, you can make better systems because human beings have not, for example, in that domain, thoroughly looked at so much data. Like if I'm detecting fraud, human-built systems or rule basis for fraud detection in a financial context may have hundreds of rules, thousands of rules. Whereas if I actually look at last X number of years of data thoroughly and have a machine learning system do it, I can make millions of rules, which has a much better, finer granularity, much faster speed than a human-designed fraud detection system might have. So the improvement is scale. Improvement is the amount of data we look at, etc.
Thank you.
Yeah, thank you. Mr. Kannan?
Professor, I was thinking like what today traditionally, if we go by this rule-based system, whatever the decision making is happening today, when a machine learning happens, it can also be optimized, right? Maybe the way we are looking at this is completely different. Maybe there is a different way to look at the end result rather than looking at the traditional way what we are looking. Does machine learning actually help in that?
What is the end result you're looking at? What kind of
whatever today there is a traditional end result, whatever with the human intervention we are having. Okay, like for example, whatever you're showing in the screen, there are three steps of human intervention. Okay, so assuming there is a machine learning, that three steps of human decisioning itself can be looked at.
Yes. We do. All I am saying here is that you can take any workflow and you can deconstruct it first into compute automation and decision automation. It's possible that you can optimize that workflow itself. Some of these tasks may be not necessary. Some of the human decisions may be not necessary. And that you do using prescriptive analytics. You say that, let's say, for increasing the profit margin, I need to cut my turnaround time. And to cut the turnaround time, I have to change the process. So that kind of optimization of the workflow itself can be there. And then can you go into an individual task? Yeah.
Can you just add to what you're saying? So that I don't miss the flow. You're saying to optimize my cost, I will do a particular activity. Maybe I will reduce my human resource. That is the thought process which we are having today, let's say, basis this human decisioning. When an ML happens, that itself could be a wrong decision. That could be a third way of reducing a cost rather than reducing this, right?
Yes. So, when you want to optimize a workflow, Mr. Kannan, it's a specific problem where you will look at millions of variations of the workflow and look at which workflow gives you the lowest cost, best turnaround time, best accuracy solution. And some of these objectives can be conflicting. So you will try to get the best balance. That is workflow automation. Workflow optimization section. Here, what we are saying is that every time there is a decision, an easy way to understand machine learning is every time there is a human decision in today's processing, there may be an ML model involved there. So if there is a traffic police, we used to have in older times, it's not always lights. There used to be people standing at the intersection and routing traffic. It's a human decision of what segment to allow to move next. And that then is a machine learning model. you can have, it is a classification problem. You can look at all the data that is involved in that and have them take a decision. If a front office executive in a clinic is setting an appointment for a patient with a particular doctor, if there is a human decision involved on which doctor to pick, then that is a decision that can be given to an ML. So I am just, at a very high level, I'm pointing out that every time there is a decision automation involved, you can think that there is an ML model that can solve.
Fair.
Does it make sense? Okay.
Yes.
Thank you. Let's move now to the next piece, which is a detailed comparison between how IT projects work versus how ML projects work. On multiple axes, we're comparing the first column is IT, the second column is ML, and we are comparing, what do these projects focus on, what kind of business knowledge is required, what schedules, what kind of risks, what kind of progress metrics, etc. I won't go through the slide, but I thought that a reference list like this will be useful. But in the interest of time, let me move to the next one. We are interested in learning ML. What would be the right way to get started on learning ML? Of course, through a course like this. But even before that, when we are discussing algorithms, you will see probability being mentioned. Some linear algebra constructs like matrices may be mentioned. Some calculus concepts like differential equations may be mentioned. So for a person that wants to understand machine learning algorithms technically, that wants to get a deeper technical intuition onto how machine learning algorithms work, these areas of mathematics will be useful. Not very sophisticated, like high school calculus will be more than sufficient. Matrices are important. Some amount of probability theory is important, etc. This is for people that want a technical intuition into the methods. For people that want only a functional intuition, which is what type of problems is this method good for? Can I apply a k-nearest neighbor in this context, or can I not? Is regression the right method to apply in this context? To answer that question, you don't need to know any of these. In this course, we will be giving you adequate intuition to say that a particular method is sufficient here. A particular method is likely to perform very well here, better than other methods. That intuition you will get yourself. And then there are a bunch of books. I am giving a few references here. There are a lot of resources. In fact, if today, if I am trying to learn, let us say, linear algebra, let's say if I have never learned linear algebra in my career, and I see here, what's this prof saying? We need linear algebra for this course. We don't. We only need it if you want a deeper technical intuition. But let's say you want to learn, pick up linear algebra. Today, I won't go to a textbook. I would go to an LLM and say, imagine that I've never studied linear algebra. Imagine that I am a, let's say, high school student. In very simple terms, explain to me what linear algebra is. And I'll sit for an hour with an LLM and I will get what I want for linear algebra. But if you want reference books that you want to look at different topics in machine learning, like today, I showed the curriculum. In the curriculum, there are things like ensembles, artificial neural networks, SVM, some terms that I have thrown at you. If you want to know what they are in good detail, for example, Christopher Bishop's text would have one chapter on ensembles, one or more chapters on ensembles, one chapter on different topics that we are covering in this course. So these will be decent books to look at. Let's look at the questions. I don't know who came first. Mr. Kannan?
No,
No,
I'm
I'm
sorry,
sorry,
I
I
lowered
lowered
my
my
hand.
hand.
Okay,
Okay,
Mr.
Mr.
Bansal.
Bansal.
Prof,
Prof,
how
how
difficult it
difficult
will
it will
be
be
for
for
me
me
to
to
get a
get a
concept
concept
on
on
high
high
school
school
calculus? So
calculus?
the
So the
rest of
rest
it
of it
maybe I
maybe I
know,
know,
but
but
maybe I've
maybe I've
forgotten
forgotten
about
about
calculus.
calculus.
So
So
if I
if I
want to
want to
maybe
maybe
spend
spend
dedicated
dedicated
days, how
days,
much
how
time
much
will
time
it
will
take
it
for
take
me
for
to
me
do
to do
that?
that?
Um,
Firstly,
firstly, to
to
understand
understand
machine
machine
learning
learning
methods
methods
intuitively,
intuitively,
you
you
don't
don't
even
even
need to
need
do
to do
that.
that.
I
I
believe
believe
that
that
by the
by the
time
time
you
you
are
are
done
done
halfway through
halfway
this
through this
class,
class,
you will
you will
know
know
what we
what we
mean
mean
by
by
let's say
let's say
gradient
gradient
descent.
descent.
Descent
Descent
uses
uses
differential
differential
equations,
equations.
but
But
we
we
don't
don't
need to
need to
understand the
understand
differential
differential
equations. You
equations. You
need to
need to
understand
understand
what
what
gradient
gradient
descent
descent
is,
is,
and I
and I
will
will
be
be
explaining
explaining
that
that
visually,
visually,
so
so
trying to
trying to
provide an
provide an
intuition
intuition
visually
visually
into
into
gradient
gradient
descent.
descent.
That
That
may
may
be
be
adequate
adequate
for
for
the
the
if you
if you
want to
want to
just
just
understand
understand
how
how
a
a
regression
regression
works
works
or
or
how
how
artificial
artificial
neural
neural
network
network
works.
works.
Both of
Both
them
of them
use
use
gradient
gradient
descent.
descent.
But if
But
you
if you
want
want
to
to
deepen
deepen
your
your
knowledge in
knowledge in
that,
that,
and if
and
you
if you
want to
want to
do
do
simple
simple
differential
differential
equations and
equations and
partial
partial
differential
differential
equations,
equations,
those
those
two
two
are
are
part of
part
the
of
high
the high
school
school
calculus
calculus
piece
piece
that
that
we are
we are
talking
talking
about.
about.
I
I
would
would
say
say
today,
today,
each
each
person will
person will
have
have
their own
their own
pace of
pace of
learning,
learning,
but
but
a
a
few
few
hours,
hours,
four, three,
three,
four
four
hours
hours
should be
should be
more than
more than
adequate
adequate.
That would be
That would be
great.
great.
Yeah.
Yeah.
So
So understand,
you
you have to
understand
understand
what
what
we are
we are
covering in
covering in
this
this
course.
course.
I'm not
I'm not
saying to
saying to
learn
learn
all of
all
high
of high
school
school
calculus.
calculus.
great.
Great.
That
That
and
and
that is
that
a
is a
time
time
that
that
at
at
least I
least
am
I am
ready to
ready to
spend.
spend.
If I
If I
can
can
get
get
something
something
on
on
what I
what I
need to,
need to,
how I
how I
need to
need to
start,
start,
and
and
what it
what
will
will
take for
take for
me to
me to
do
do
it,
it,
that will
that
be
will be
great. So
great.
I
So
can
I can
spend the
spend that
time
time
over
over
next
next
week.
week.
Yeah.
Yeah.
When I
When I
give the
give the
synopsis,
synopsis
for
for
every
every
topic, you
topic,
will
you
know
will know
what is
what is
going to
going
be
to be
covered.
covered,
And for
and for
some of
some of
them,
them,
I'll
I'll
also
also
include
include
a
a
learning
learning
resource.
resource.
Yes,
Thank you,
Yes,
sir.
Mr.
Mr.
Thank you
Raghuram.
so much.
Raghuram.
Miss
Miss
Raghuraman.
Raghuraman.
Professor,
Professor,
I
as
I was
I was
just
just
thinking
thinking
of
of
your
your
learning
learning
comparison
comparison
chart
part
slide
slide
earlier,
earlier,
and
and
how
how
traditional
traditional
programming
programming
and
and
machine
machine
learning
learning
are
are
compared
compared
with
with
each
each
other.
other.
I
I
was
was
just
just
wondering
wondering
whether
whether
typical
typical
outputs
outputs
of
of
an
an
ML,
ML,
is
is
it
it
more
more
limited
limited
by
by
the
the
data
data
quality
quality
or
or
more
more
by
by
the
the
program or
program or
model
model
that
that
the ML
the ML
develops?
develops?
Or is
Or
it
is it
even
even
right to
right to
look
look
at it
at it
that
that
way?
way?
Yeah,
Yeah,
it's
it's
very
very
right to
right to
look at
look
it
at it
that
that
way.
way.
And it's
And
a
it's a
great
great
question.
question.
You
You
remember when
remember
I
when I
talked
talked
about
about
natural
natural
learning,
learning,
I
I
said there
said
is
there
a
is a
predisposition
predisposition
that
that
things
things
are
are
born with.
born with.
It could be a
Could be a
genetic
genetic
predisposition.
predisposition.
Like
Like
that,
that,
there
there
is
is
what we
what we
do is
do
we
is we
impose
impose
restrictions
restrictions
on the
on the
types of
types of
models we
models we
can
can
learn,
learn,
on the
on the
types of
types of
programs we
programs we
can
can
build.
build.
So,
So
if
if
you
you
say
say
a
a
regression
regression
model,
model,
we are
we are
only
only
looking
looking
at,
at,
let's say, a
let's say, a
linear
linear
regression
regression
model.
model.
We are
We are
only
only
looking
looking
at
at
straight
straight
lines.
lines.
We can
We can
learn
learn
straight
straight
lines in
lines
two
in two
dimensions,
dimensions,
three
three
dimensions,
dimensions,
100
100
dimensions,
dimensions,
but we
but
can
we can
only
only
learn
learn
straight
straight
lines.
lines.
And
And
if
if
you're
you're
looking
looking
at,
at,
let us
let us
say,
say,
nearest
nearest
neighbor,
neighbor,
all we
all we
can
can
learn
learn
is
is,
given an
given an
example,
example,
what are
what
the
are the
other
other
examples
examples
close to
close
it?
to it?
So,
So
similarity
similarity
is
is
what we
what we
learn,
learn,
nothing
nothing
more.
more.
So,
So
the
the
classes,
classes,
the
the
reason we
reason we
have
have
so
so
many
many
sets of
sets of
machine
machine
learning
learning
methods
methods
is
is,
in
in
each
each
one,
one,
we
we
are
are
imposing a
imposing a
predisposition
predisposition
that
that
only
only
this
this
type of
type of
model
model
can be
can be
learned.
learned.
In
In
that
that
predisposition, the
predisposition, the
equivalent
equivalent
word in
word in
machine
machine
learning is
learning is
bias.
bias.
So,
So
we
we
introduce
introduce
models of
models models of a certain type, and that method can only learn that models. So what that means for a machine learning practitioner is pick the right model first. Once you pick it, give it the right kind of data so you can train it, but the maximum you can do is whatever is allowed within that predisposition, within that bias. You can only learn lines if you pick the regression model. If you pick an artificial neural network, you can learn arbitrarily nonlinear surfaces. So picking the program is very, very important. The typical sequence is you pick the type of models you want to generate, which is the class of models you want to generate, and that's what is this division of our curriculum. It is different models. We are looking at clustering models. Association rules is a type of model. Time series is a type of model, etc. So you pick the type of model, and then you pick the adequate data to learn that model. Both you need to do the selection of.
So then it can be limited by both.
It can be
Even
limited
if I
by
pick the right model, the quality of the data might be limited. And even if the data quality is right, the model is just not picked up right in alignment with the
So
data.
today you have a yes. So today on the second problem where you said I have the right kind of data, but I'm limited by the model. Today you have you use AutoML. AutoML is a automation framework where you look at all possible families of models in sequence because you now have the compute. So you dump the data into an AutoML system. It'll run whatever long time it needs to run for and come back to you saying, for this data, this is the best type of model to use. In that, these are the parameters that I have computed. It solves both problems.
So then the both the limitations are resolved.
Not both. Data is still a limitation. The model limitation is resolved. Because it won't go and make up new data. That's another thing which is called active learning. Active learning methods can create their own data, can tell what is the next thing you need to solve this problem. We used to have, I don't know if you played this. I saw people playing it. I played it. Let's say you have a puzzle you're trying to solve or an investigation case you're trying to solve. You want to ask the next question such that you have maximum amount of information. Like a 20 questions. It was, the game was 20 questions. So what is the data point I need next, which I don't have currently, which will add maximum value to my model? This kind of thing is called active machine learning. So your AutoML can solve the problem of method dependence, and active learning can solve the problem of data partially. And because there are limitations anyway of, data has to be observed and gotten, recorded and gotten. So there's always a limitation on that. Yeah. Mr. Ashish Kumar.
Thank you.
Thank you.
Yes, sir. Good evening, sir. Sir,
Good evening.
I want to know in real-time fraud detection or transaction monitoring, what should we use in banking, ML or AI, agentic AI?
Okay. Both have their, your question is like, I have a screw that I need to screw in. Should I use a screwdriver or should I use a power screwdriver? Both can be used depending on what it is that, depending on your data, number of, the constraints you have, etc. But so it's never a decision between, ML versus the generative AI, agentic AI frameworks, but it is, I want to solve this problem within this cost. This is the compute cost I'm willing to put. Like for example, my bank, I'm taking a transaction fraud detection example that you said. I can say my bank has 100 million transactions it needs to process on a daily basis. I'm just taking a hypothetical number. 10 million transactions it needs to process on a daily basis. For that 10 million transactions, if I were to use an LLM, for each transaction, there are so many tokens I will spend, hence my total cost will be this. Instead, it may be possible for me to generate a fraud detection model using the symbolic ML method, like a decision tree or a random forest or an SVM, whatever. And if I implement that on my own hardware, then I don't need to incur a token cost or LLM calls or overhead. So it's the question is on resources, not on capability of algorithms. You take the decision based on resources. And as we go through the course, we will see the resource consumption. In this course, we will see for symbolic methods. And as we go into future courses, we will see in detail for the agentic AI, Gen AI combination systems.
Yeah.
Yeah. Okay.
Thank you. Thank you.
Yes, thank you. Mr. Inyama?
Thank you very much, Doctor. So, Doctor, I don't know if this question is essentially is for you, but is stemming from an observation I had from the forensic analysis I did of the evolution and the current status of AI with respect to what I term as infrastructure constraint migration. So, since this program is about emerging technologies, does it have to do with only technologies in the sphere of IT? That's my primary question.
So this is a emerging technology program on with specialization in Gen AI. So usage of AI in any domain is fair game. So if it is physical AI, if there are factories, physical systems where you are trying to improve productivity, speed, turnaround time, quality using AI, it's fair game. It need not just be corporate IT. But of course, any AI models that you implement will run on computers. They may run on edge devices, they may run on fog devices or cloud computing and so on. But it will be on some kind of a compute infrastructure. That way, it will be information technology. I don't know if I'm answering your question.
Pretty much, yes. Pretty much. Yeah, pretty much. Yeah, so I just wanted to also share that one of the physical infrastructures that seems to have integrated very much with the AI evolution is the infrastructure of power. And power infrastructure, general power infrastructure availability for the execution of AI itself and the transmission of AI systems, whether for data centers or even to drive models themselves. The massive
I
model.
understand what you're saying.
Yes. So and they have integrated so very much that you can't really separate them as in like they kind of like move together.
So in different courses in this program, we will be touching upon AI applications for the power and utilities sector. So how do you improve power infrastructures, decision making, real-time decision making in power infrastructures using AI? We'll be touching on some of those applications. And when we do LLMs in the generative pre-trained models class, there is going to be a LLM ops portion where we will actively look at costing. And costing, power is an integral part of that. So power utilization. When we have in the responsible AI course, we'll be specifically looking at sustainability and responsibility towards the planet. That is power consumption, other energy consumption. We will be looking at that as one axis, taking specific projects and looking at how they fare in terms of power energy utilization. So two things: AI for power sector, power for AI sector. Both are to be looked at. And AI for power sector typically is seen in as part of applications. We will look at examples. And power for the AI sector, which is a very important consideration, and we know all kinds of extra planetary efforts are being planned for power, as data centers in space, data centers on another planet, and so on. So power for the AI sector is an important consideration, and that gets touched. That topic gets touched in generative pre-trained models class and the responsible AI course.
Oh, okay. Thank you.
Okay.
So because I was going, I'm also looking at the emerging technologies in that sector because it also needed to as a sustainable framework for the AI technology as well.
Yes.
Unless
Thank you. Yes.
if we're able to have a breakthrough for optimized power optimized processors, GPUs.
Yeah,
I mean,
there is a lot of work happening in that front. In fact, I would say there are billions of dollars being invested on solving power billions. Why billions? I think even hundreds of billions of dollars being invested into solving the power problem, because that is the immediate roadblock for the growth of AI. Let's move on. I'll go to Mr. Khedkar's question, please.
thank you, sir.
Hello, Dr.
Thank
Mohit.
you.
My question was regarding the previous discussion which we're having regarding the fraud detection use case regarding the that part. So when we were talking about it, the options which were means based on my volume of the task which is at hand and how much money I can spend on that. So if I say that I deploy a deterministic the methodology for classification in the first half and second half, then I go into much deeper fraud detection use case. That will reduce the volume of the that particular part. So this kind of hybrid mechanism when we
Absolutely. Yes.
so yeah. So when we
There are hybrid architectures where we utilize symbolic AI for certain types of to route certain type of transactions and only take it to LLMs or agents for certain subset of transactions, because per transaction cost is more. So hybrid systems to optimize the cost, that is something that people have been looking at. We will be commenting on that in the future courses.
okay, thank you.
Yeah. Okay. Let's the time that is remaining. Let us at least look at the definitions of these three methods: supervised learning, unsupervised learning, and reinforcement learning. For supervised learning, we require data with some ground truth labels. What is a ground truth label? Knowing that patient with these measurements has this diagnosis is a ground truth label. Knowing that student with this kind of data, learning data, has interest in this field, or counseling has been conducted to the student and this is what they pick. That is ground truth. So data with ground truth labels is necessary for supervised learning. Data without labels is sufficient for unsupervised learning. But for both of them, it is only data that they see. They don't see any other world, any other environment. Supervised learning and unsupervised learning, both of them, their entire worldview is just the data you give them. They don't know any better. They have only seen this data, and from this data, they try to build the best possible model that they can. Supervised learning or unsupervised learning. Whereas reinforcement learning has a peek into the environment. It knows what reward. It has a concept of reward and punishment, or reward, positive reward and negative reward. And this is reward being received from an external entity, which is the world. So as the model is, let's say, as a drone is flying, let's say if we are using reinforcement learning to train a drone to fly, as the drone increases its height, at a certain point it hits a, let's say, a tree branch or the roof of the room. That is a reward, a negative reward it got because it bumped itself against something that is above. So next time, or over a period of time, it learns not to fly that high. because there is a negative reward there. So there is an entity that is giving positive reward or negative reward, and this is happening. This entity is the world. So this is happening as the system is learning. So live, the rewards are being given, and the system itself learns. The system itself knows that it can go through X number of states. So a drone knows that it can fly up, it can increase its height, it can decrease its height, it can move to the right, it can move to the left, it can shut itself off. It knows that it can be in certain states. In each state, it knows what actions it can take. Okay. Based on that, a reinforcement learning, gives the output, which is what is the right action to take in this stage. At the current moment in time, what is the right action to take? That's what a reinforcement learning system gives. Whereas in supervised learning, the output that is given is a mapping from the data to the labels. And in unsupervised learning, it is categories of dividing this data. The data can be divided into different categories. What are those categories? What are those clusters? Is what an unsupervised learning gives. So to make it visually more clear, unsupervised learning, if you're given all these points, an unsupervised learning can tell you that this seems to be one cluster of points, this seems to be another cluster, and this seems to be a third cluster. It may be uncertain about points that are between clusters, more certain about points within the cluster, but essentially you are given, imagine the same picture with all points as black. That is the input to unsupervised learning, where only the data set is given, no ground truth labels, and it divides the data set into multiple classes or multiple categories. This is what unsupervised learning does. Supervised learning, once you give these sets, finds the surface that separates them. The line that separates green points from blue points. The surface that separates green from blue from red. Which could be, let me just draw that, which could look like, I will just attempt a lousy drawing here. Let's say something like that, and that. Maybe supervised learning, when you give it the data points with labels, it can find the surface that is separating. The surface can be as simple as a single line, or it could be a non-linear surface separating multiple multiple classes. So unsupervised learning takes just data and divides it into clusters. Supervised learning takes these clusters, finds surfaces, decision surfaces that are separating the classes. Reinforcement learning has a set of classes and transitions between them, what actions you can take at each class, and it learns what is the next best action to take. Okay, reinforcement. So three types, and we are having a more detailed comparison between all the three types of learning below. I'll leave you to read that. So this is this differentiation between the three types of learning. So some key concepts of learning. I'll come to you, Mr. Arora. I want to finish this slide and then answer questions and wrap up the class. Some key terminologies we will hear throughout learning. I mean, we will learn multiple methods of unsupervised learning, multiple methods of supervised learning, and we'll also look into reinforcement learning in more detail. This class, I just wanted to introduce what each one is. Some key concepts of ML which you will hear throughout is one is the curse of dimensionality. We will discuss this more in the coming class, next Saturday's class, when we talk about data. Curse of dimensionality basically means that In two dimensions, 2 points may be well separated. Let's say if I have a small cloud of points here and a small cloud of points here, I hope you can see my video. In two dimensions, they may be nicely separated. Even in three dimensions, you may be able to see the separation well. But if I add 100 spurious dimensions to this data, then they will no longer remain clusters. They will be all over the place. As dimensions increase, as we go to higher dimensional data sets, distances don't make sense. Separation doesn't make sense. Because in higher dimensions, everything is more or less equally far from everything else. That is what is curse of dimensionality. As you increase dimensions, data points become harder and harder to, sets of data become harder and harder to separate. That's curse of dimensionality. And you need to design methods taking that curse of dimensionality into effect. This is one key concept that you'll see. Overfitting is another concept. Overfitting just means that, I've been given the data of 20,000 patients, and I built the best possible model for these 20,000 patients. I have 100% accuracy. I built a fantastic model for diagnosing these 20,000 patients. Now you give me 100 more patients data. The same model, which does so well on my 20,000, for the new 100 patients data that have come in, this model doesn't do as well. It has much lower accuracy of these new points. That is called overfitting. You fit your model to the training data you have seen. You didn't fit it well to generalize. You didn't fit a model that generalizes well. So this is something that we need to keep in mind while we are learning machine learning. Our goal is not to do well on the data we have today. Our success is if the model we build today continues to work well for new data which is coming in. We know that we have built a good diagnosis model. Let's say a doctor knows, a human doctor knows that they have learned to diagnose a fever well. If even as new patients come in, let's say the doctor is staying in a particular city, in a particular country. Let's say in that city, as new patients are coming in, this doctor's diagnosis is correct. Yes, if you move the doctor to a very new situation, to a different country, to a different city, and the types of fevers there are very different, this doctor might fail. That's okay. As long as the new data is coming from the same distribution as the old data, the model should work well on the new data. That is called generalization. As long as it is coming from more or less the same distribution, your system should work well. Like it is, as long as you're predicting rain from last 10 years of rain, you're predicting next year's rain. It's probably coming from the same distribution because it's the same planet, same weather variations that you have seen for 10 years, etc. But if there is very strong global warming and rain patterns fundamentally change, then your model could fail. That's okay. But as long as data is coming from the same distribution, you should do well. That means that you should not overfit, you should generalize well. Those are the two terms that we will see in ML. Let me pause there, Mr. Arora.
Yeah, in your previous slide where you introduced the three kind of trainings, supervised, unsupervised, and the reinforcement one. Now, I understand that how this works in terms of supervised. I mean, maybe during the learning process, they give you photographs of various kind of cats, and then you are asked to recognize that, okay, this is cat, and the machine is able to recognize, and that may categorize into supervised learning. Similarly, there's an unsupervised learning where you're given different kind of animals, and then you're asked to categorize them into multiple categories, and then you have reinforcement. Now, each of these models would have some base data from where they start, right? For example, an unsupervised learning would have to know how to categorize elephants separately and cats separately and maybe another object separately. So, how does that work? And I'm sure for reinforcement learning also, there is some base data, and then reinforcement is basically like you talked about penalty and rewards. It's learning from its mistakes. If it's making a mistake, it's a penalty. If it is correct, then it's a reward, and it's learning on its own. So, what about that base data? How does that happen?
We will, of course, see this in more detail when we discuss unsupervised learning. But what we are looking at in unsupervised data, they don't tell you what animal they have given. They just give you images of 10,000 pictures of animals. You don't know how many animals there are in that. You can't recognize what, you don't know what those animals are. Nobody gives that data. So what we are assuming is that, let's say these are 1,000 by 1,000 images. We are assuming that there is a way of extracting information from these 1,000 by 1,000 images. Let's say we condense it into a 40 features space. So there is a 40-dimensional space in which each of these photographs, 10,000 photographs that are given to you, becomes a point in a 40-dimensional space. So these points, there are some points that are close to each other, that are clustered, some points that are separated from each other. So like this, you will see that there are clusters in that 40-dimensional space. No other data has been given to you. All you have is this image, and you have a way of condensing it into this 40-dimensional thing which is called the feature space. You take the raw data and put it into the feature space. Once you put it into the feature space, you see some patterns. This pattern is these points are close to each other, these points are separate from each other. That's all is the pattern. So you will then see maybe all of these points correspond to the same animal. Maybe all of these points correspond to the same animal. It's a guess you are doing. You still do not know why you are calling all of them as same, except for the geometric distance and the geometric clustering of the points. You don't have any other clue that they are the same animal. You run this unsupervised learning first. After that, now you have a bunch of things. We are calling this as animal 1, animal 2, animal 3. Now you can go to a supervised method and say, build me a decision tree that tells what is different between animal 1 and animal 2. What is different between animal 2 and animal 3. That is these surfaces that you are finding. So it says that if it gives you an equation of a line, and it says if it is to the right, then it is animal 1. If it is to the left, then it is animal 2. Or you may do an if-then rule. If x is greater than so much, y is less than so much, then it is animal 1. So base data is just the images that are given to you and your ability to move those raw data into a feature vector of 40 dimensions. We'll talk about this more, so let's not dwell on this now. We will talk about it more, but basically that's the base.
And in reinforcement, is it a mixture of both? And how is the base data coming?
No. Reinforcement, it is like I take an image and I, arbitrarily, let's say I'm blind. Okay, let's say my eyes are closed. And I take an image and I call it a cat. If it is right, then I get a positive reward. If it is wrong, I get a negative reward. Okay, so I'm seeing data, making the prediction, and then I'm getting a reward or punishment based on which I'm learning. I'm gravitating towards doing the right predictions. We'll look at this in more detail. Don't try to understand it now. I'm just introducing these terms. We'll have detailed classes to understand. Let's quickly close it, Mr. Bhaskaran, and then Mr. Raguraman, and we'll close the class.
Yeah, so on your next slide, if you have to avoid overfitting and do the right model selection, isn't strategies for the right sampling of data, having the input data have the right distribution, isn't that important?
It's very important. Yes, it's very important. I'm only introducing some terms in ML here. Overfitting, generalization, dimensionality. We have not gone into the process. Absolutely, sampling is important. Feature selection is important. And then selection of the method is important. then you need to have metrics for error measurement. Those are important. We'll go through those stages. Okay, Ms. Raguraman.
Professor, in unsupervised data, in unsupervised learning, you had mentioned that the data gets categorized to clusters depending on what are the common features and so on. What happens to data overlaps? That is, there could be certain data points which have, say,
if they're overlapping all 40 dimensions, let's say we said, for the images example Mr. Arora asked, I said, let's say every image you're taking into 40 dimensions. Let's say if your points are, if two clusters are overlapping on all 40 dimensions, then it means that maybe you have less features. Maybe that 40 should become 50, 60. Maybe you need to find dimensions where these points get separated. So maybe your description is not fine-grained enough. Right? So when we are doing, one of the things that unsupervised learning tells us is if the feature space we are operating in is adequate or not.
Okay. So if there were overlaps, then it will throw up a requirement saying that you may need to add more features in order to make it more granular.
Yeah. You can use that as a tool for this purpose. It will anyway give you clusters, even with the overlaps, and it will say for some points that the classification is uncertain. So if there is uncertainty, you can alleviate it by adding more features, and so on.
Yeah.
Okay. So
So
we
it's
are
like your 20Q example, right? Even with 20 questions, if you're not able to find, add more questions.
Yeah, exactly.
Yeah.
Correct, Mr. Bhaskar. So we are 13 minutes above the class time, so I will stop here. I'll of course upload this presentation and the synopsis before the next class. I'll also ask Dr. Saroja to upload some details about the platform that she's going to be utilizing for the benefit of those that didn't attend the first demonstration by her. Okay. Thank you so much. You have a great week, all of you.
This has been a super lecture, Dr. Murthy.
Thank you,
Thank you,
Dr.
Dr.
Murthy.
Murthy. It's been
Thank
Thank you so much.
Thank
you.
you.
Thank you so much.
Bye-bye.
Thank you,
so much.
Professor. Have a good night.
Thank you
Thank
so
you.
much.
Have a good weekend.
No.
Thank you, Dr. Murthy. Thank you.
Thank you.